Hi everyone. So I thought we could do a little review day here thing, where we just sort of go back to make sure we're comfortable with all the different things. So first, the integral from 1 to 32 of x to the minus 6/5 dx. So what are we supposed to do here? Well, we see the boundaries. So pause the video, give this one a try, come back when you're done. So this is a definite integral, and with a definite integral I know I have to find the antiderivative of this, which means I'm going to add 1. So I'm going to have x to the minus 1/5 here. But you know, if I were to take the derivative of this, that minus 1/5 would come down, and I don't see 1 there. So there must be something here on our potential antiderivative so that when I take the derivative of it, the coefficient cancels. So I could write 1 over negative 1/5, but I just assume use the reciprocal, so negative 5 over 1. Because now when that negative 1/5 comes down, the 5's cancel, the negative goes away, and I end up with this because I subtracted 1. Okay, but don't forget we need to evaluate this from 1 to 32. So we've got negative 5, 32 to the negative 1/5 minus negative 5, 1 to the negative 1/5. Remember that 32 is the same as 2 to the 5th. When I raise a power to a power, I multiply them. So this is going to turn into 2 to the negative 1, or 2 on the bottom, plus 5th root of 1 is 1. 1 over 1 is 1, so we end up with 1. So that's going to be negative 2/2 minus 5 plus 2 is minus 3/2. All right, well, there's the first one. Let's keep going. What about find y prime, given y equals the integral from 0 to x of square root 1 minus t squared dt. So in order to find y prime, what do I need to do? Pause the video, give yourself this practice. Hey, welcome back. So I'm taking the derivative of both sides with respect to x, and I know that derivative undoes integral, and this goes in there. Square root 1 minus x squared. Don't forget, take the derivative of that. Here it's just 1, we really don't need to worry, but anytime my derivative of that is going to be something other than 1, yeah, definitely need to show it. Now, this is taking a derivative. This is not an indefinite integral, so please don't even think about plus c here. Okay. And this one, how would you do this one? The integral from x to the third to 4 of ln of t dt is what y equals. And again, I want dy dx. All right, give this one a try, see what comes of it. Welcome back. So I hope you thought about flipping these boundaries and pulling out that negative, because we really want this number down here always to be a constant. All right, now we've got ln of t dt. So now when I take the derivative with respect to x, I'm taking the derivative with respect to x. Derivative undoes integral. This goes in there. Don't lose that. So ln x to the third. But look, lo and behold, chain rule says don't forget to take the derivative of that, 3x squared. And so there's our answer. By the way, don't box in your answers. It's not a good habit. if you're taking the AP exam. Because when you do that, then suddenly you're claiming that to be your final answer. Okay, integral 3x, 2x to the third, secant t tangent t dt is y. And of course, I'm looking for dy dx. So, take that derivative. Hey, welcome back. So, I'm going to take the derivative with respect to x on both sides. Derivative undoes integral, but oh, a constant. All right, well, so let's hold on the derivative for a moment, and let's apply our integral properties to rewrite this first into 3x to some constant. 0 is just arbitrary. Secant t tangent t dt plus the integral from 0 to 2x to the third. Secant t tan t dt. Okay. I've got that constant down at the bottom that I want. Alexa off. Going to my variable of differentiation, but I don't have that here. So I think I need to pull out a negative and flip my balance. So now when I take the derivative here is going to be secant 3x tangent 3x times the derivative here. Don't lose that negative. And one other thing. So, yeah, this, when you take the derivative, goes here and here. Not just one of them, and definitely in both of them. Because those are common mistakes I see where a student does this, secant 3x, the tangent x for some reason. Or they make them both x, even though this says 3x. So do watch out for that. And we still have a plus sign, and we're taking another derivative here. So when I do, it's going to be secant 2x to the third, tangent 2x to the third, times the derivative of that inside function, 6x squared. All right. So please make sure you're comfortable with using FTC Part 1. Remember, FTC Part 1, Fundamental Theorem of Calculus Part 1, is all about taking the derivative of an integral. Okay. Now, what about this one? 0 to 1 square root 1 minus t squared dt. Will you please do this problem? I kind of want to draw a picture of what's going on here. Huh. I think that's closer. Still not good. Oh my goodness. There. Okay, 1, negative 1, 1 up here. And we're looking for the area between the curve and the x-axis from 0 to 1. Okay. So, how do I evaluate this? Well, so here's the thing. Whose derivative is this? Do you remember? I hope so, because you need to recognize that this is inverse sine of t. Plus c, well, it's a definite integral because it has boundaries. So those c's are going to go away, which means I'm just going to leave them out at the beginning. So I want to evaluate inverse sine from 0 to 1. Now, no kidding. I know you don't believe me, but this isn't our final answer. You're supposed to know what angle within the restriction of inverse sine has an upness of 1. And you're supposed to know what angle within the restriction of inverse sine is 0. And so I end up with pi over 2. Okay? Yeah, you might really actually want to, take a little time and go back and look at that section on inverse trig functions and evaluating them. No, really. All right, so this was part A. Part A was find this integral. Part B is what's the average value of 1 minus t squared on 0 to 1. And think about what we're asking here. This is what's the average y value. And I've got all these y values. Highest one is a y value of 1. The smallest one is a y value of 0. And we go through an infinite number of y values between those two. So we want to know what that average value is, what that average y value is here. Well, let's use our average value formula. 1 over b minus a integral, oopsie, thank you. We're only going from 0 to 1. And notice when I have this integral 1 over t squared dt, we've already done this, right? We already know that that's sine inverse of t, and we want to evaluate from 0 to 1. Well, isn't that interesting? This is exactly what we had before. Now, the numbers, the units are going to be different in this situation, right? Because in the last problem, we were finding this area. But now, we're just finding a length. Okay? So be mindful of that even though these numbers are going to look the same, they're both going to look like pi over 2. This one is pi over 2 units squared. And what's the average of these heights? The average of these heights is pi over 2 units. So this is 1. Wait a second. No, that can't be right. Because pi over 2 is 1.57, and that's much higher than what happens if I plug a 0 in there. Did I miss something? What happened here? Let's take a second look. Okay, that is the derivative of sine inverse. I do want to evaluate sine inverse from 1 to 0. Sine inverse of 0, what angle has an upness of 0? 0 does. And over here, what angle within the restriction for inverse sine has an upness of 1? It's definitely pi over 2. And I would think maybe something over here. Maybe it was my 1 over b minus a, but that's just 1. Huh. I find that very strange indeed, because that is a semicircle. That's quite boggling to me. I have an idea. Let's try magic calculator box. So we're going to type in square root 1 minus x squared. And I'm going to go back to the main screen. And what I think might be helpful for me is to go back and evaluate the integral from the very beginning and see what happens there. Int 1, comma, x, comma, 0, comma, 1. I think it's thinking. There we go. It's pi over 4, not pi over 2. Well, what did I miss when I did that integral? Oh, you know what? I feel so very stupid. Oh, my goodness. It's just impressive how sometimes it happens to everybody. In particular, hey, this is a quarter of a circle. Why aren't we just doing 1/4 of pi radius squared? Oh, mercy. Yeah. So, that's the way I would do that. And because of that, I think maybe I need to go back and review my derivatives, because something wasn't working there. And I'm kind of interested to know what has occurred. Yes, what is the derivative here? Oh, 1 over square root. That's why. This is the derivative of sine inverse of t. Not this. Yeah. Okay. So, hey, there's no excuse for being asleep, Mr. Gukla. This is a semicircle, and you need to appeal to the geometry of the situation. Now, I do want to say, while that was, just a terrible fail on my part for a moment there, I do want to say that that process of thinking your way through and that process of taking an alternate direction and definitely not giving it to soul-crushing depression and anxiety, maybe that was the best thing I just showed you. Don't freak out. Okay, what's next? Talked about those. Ooh, how about some total area problems? Find the total shaded area. And here's our first one. This curve is sine x. This is pi over 2. And we're looking for this shaded area. And again, there are a couple of ways that you could go about thinking about this. So maybe you want to do it 2 different ways. I'll see you in a few minutes after you've given it a try, and let's talk about it. Okay, welcome back. So the way I don't like to do this is to find the area of this rectangle whose height is 1. And I know that because when I put a pi over 2 in there, the sine of pi over 2 is 1. So this line must be equals 1. And I know that this length goes from 0 to pi over 2. So this is pi over 2. And so I can think about this as this big rectangle, area of the rectangle, minus this down here. If I have this big rectangle and I take away this much area, which happens to be the integral from 0 to pi over 2 of sine x dx, that will be this shaded area. And we can definitely do that. 1 times pi over 2 is pi over 2. And the integral of sine is cosine, so minus cosine x. And I want to evaluate from 0 to pi over 2. So we're going to have pi over 2 minus cosine of pi over 2 is 0. Cosine of 0 is 1. And so I get minus a minus or a plus. And so that's going to be 1 plus pi over 2 for here. This is what I believe. Subtract it. Yes. All right, well, let's just test that theory by doing it the way I would prefer to do it, which is to think about adding up an infinite number of these lengths. And the length is determined by this and this. in such a way that I'm doing top minus bottom. Top minus bottom gets me this length. Top minus bottom gets me this length. I'm using top minus bottom. And curiously, when I think in terms of top minus bottom, my top is 1, and my bottom is sine x. Oh, right. That was always a height of 1 as we integrated from 0 to pi over 2. So the antiderivative here is x minus cosine x from 0 to pi over 2. When I plug in my pi over 2, I'm going to get this pi over 2 here. Cosine of pi over 2 is 0. And then I'm going to plug in a 0, so this will go away. But the cosine of 0 is 1, and I'll have minus a minus 1 again. And so I end up in exactly the same place. In more complicated problems, really, I don't want to try and break this region into 3 or 4 pieces. I would much prefer instead to do top minus bottom. So let's imagine that we had this kind of thing. This is y equals x squared minus 1. And we're integrating to, not drawn to scale. We're integrating, well, I see a bunch of different things here. Let's start with this one. Okay, now I want you to use top minus bottom. And the top here goes to the bottom here. The top here is y equals 3. How did I know that? Because when I plug a 2 in here, 2 squared is 4, 4 minus 1 is 3. So the y value here must be 3, and the y value there is 3. This top is y equals 3. And this bottom is x squared minus 1. And notice as we go across, the top is still 1 equals 3, and the bottom is still y equals x squared minus 1. And that holds true all the way to the end. So if I'm thinking about top minus bottom, I'm thinking about here 3 minus x squared minus 1 dx. And I'm integrating from 0 to 2. 0 to 2. Okay, so I would take the time to distribute. I do think that's worth making this problem as less visually disrupting as possible. And look, I can combine like terms. So this can be a 4 dx. Antiderivative of 4 is 4x. Antiderivative of x squared is x to the third over 3. And we want to evaluate from 0 to 2. So that's going to be 8 minus 8 thirds minus, I plug in a 0 and I get 0 minus 0. So that's 24 thirds minus 8 thirds is 16 thirds. And so I know this combined area, this total shaded area, is going to be 16 thirds. Great. Top minus bottom, not so bad. Well, let's think of another way of doing this, because that's, in fact, often what I see students doing because they didn't bother to remember top minus bottom. So some students say, well, okay, I know that this shaded region is made up of this blue stuff. And this blue stuff is the integral of x squared minus 1 from 0 to 1. Okay, so that's going to be x to the third over 3 minus x from 0 to 1, 1 third minus 1 minus 0. Well, so that turns out to be negative 2 thirds. But wait a second, we expected that integral to be negative because it represents this below the x-axis. But we're talking about area, so I have to remember that this is going to be positive 2 thirds. Oh my goodness. Next, I would have to do this and find the area of this rectangle. I know the height of the rectangle is 3. I know the width of the rectangle is 1. And so 3 times 1 is 3. But wait, there's more. Because now I need to find this piece and add it as well. However, that's not the integral. The integral from 1 to 2 is that region down there. To find this region, I would need to do the area of this rectangle, which is a base of 1 and a height of 3, minus this shaded region, which is the integral from 1 to 2 of x squared minus 1 dx. Oh my goodness, really? You're going to do that? I mean, granted, instead of doing it as this rectangle minus this integral, I have seen a number of students prefer to do this rectangle minus this integral. So there's the rectangle. No, because now we're going over 2. This is 2 by 3 or 6, and we want to subtract the integral from 1 to 2 of x squared minus 1 dx. Oh my God, you've split this into so many pieces. Why can't you just do top minus bottom? Please do top minus bottom, okay? All right, so those area questions, I definitely think you should be comfortable with them. We'll meet them again in Chapter 7. There are these two other problems that I think we should definitely be comfortable with. They're from page 307 in our textbook. It looks like problems 57 and 59. So we'll do those two, and that'll be it for this video. Okay, so 57 comes with a picture. The picture goes like that. And then this is -2. This is 3. This is 10. And this is occurring at x equals 8. And what are we told? Oh, we're told that there's this function called h, which is a function of x, and that's equal to the integral from 0 to x of f of t dt. This is f of t. So if I integrate this curve, I get h. Okay, so what does that mean? Well, I don't know if you recall, but I definitely said in a previous video that it would be so worth your time to actually understand what it is you're looking at before you look at any of the questions. Okay? So, without looking at the questions yet, what is this? What does this mean? Well, this is the antiderivative of that. So, what happens when we take the derivative of both sides? Well, over here, I get big H prime. And over here, thanks to FTC Part 1, the derivative undoes integral. The x goes there. And I have f of x. So, this graph is h prime, not h. Please know that before you start reading the questions. First question, what about h of 0? Okay, so how is h defined? H is defined as the integral from 0 to x of f of t dt. And we want to know h of 0, which means we're replacing x with 0. Oh look, the integral from 0 to 0. We know the integral from 0 to 0 is 0. Ta-da! Okay. There's part A. Part B. When is h decreasing? Not when is this graph decreasing. This isn't the h function. H is the integral. When is h decreasing? Well, I remember saying in Chapter 5 last semester that if we wanted to know when a function was increasing or decreasing, we would look at the derivative of that function. So, when is h decreasing? Answer, when h prime, which in this case is equal to f, is less than 0. When our derivative is less than 0, we know the original function is decreasing. And I see that happening over here from 0 to 3. So on 0 to 3. That's part B. Part C. When is h concave down? When is h concave down? On, 0 to 10. Because we're going from 0 to 10. Well, remember, this is not h. This is h prime. And how do I know about concavity when I look at h prime? Well, when h prime is increasing, h double prime would be greater than 0, so h would be concave up. But we want concave down, so we want h prime decreasing so that h double prime is less than 0, so we get concave down. So when is h prime decreasing? This is a graph of h prime, and h prime is decreasing from x equals 8 to x equals 10. So on 8 to 10, h is concave down. And yes, that's my justification there. Okay? All right, what about part D? Is h of 1 greater than or equal to 0? Well, that's an interesting. Oh, and then we're asked why or why not. So let's think about this. Is h of 1 less than 0? Okay, well, we know that h of 0 equals 0. And so, I kind of want to look at this. Don't we know FTC2? Couldn't we say something like, okay, h of 1 minus h of 0 equals the integral from 0 to 1 of h prime. And what's h prime? H prime is this graph. So dx equals the integral from 0 to 1 of f. So when I integrate from 0 to 1, I'm going to get a negative number. So this integral is negative. And h of 0 we determined was 0. So I'm saying then that h of 1 is equal to the value of this integral, and the value of that integral is a negative number. So is h prime less than 0? H of 1 less than 0? Yes, because h of 1 minus h of 0 equals a negative 0 minus h sub 1. Yeah, I don't need to know what negative number. I just need to know that that value is negative for that integral from 0 to 1. Okay. With that one, E. Where does h have its maximum value? We want to know where h is a max. This is not a graph of h. This is a graph of h prime. So let's look at our h prime sign chart. We start at 0, we end at 10. Ooh, look, here's a critical value at 3. But wait a moment. H prime is negative to the left of 3. H prime is positive to the right of 3. And this is an indication of a minimum at x equals 3, not a maximum. And we were asked to find where h has its maximum value. So where else do we look besides derivative equal to 0? Well, we could also look at derivative undefined, but I don't have any undefined places on h prime. So that's not going to work. Were there any other places we should look for mins and maxes? Why, yes, there are. They're called endpoints. So from this point, h is decreasing. So I know that from this point on h, my h graph goes down because of this. That means that h of 0 is a max. And over here, because h prime is positive, I know h is increasing until we get to 10. So I've got another max over here. So we've got two maxes here. Do they ask us about, well, it says its maximum value. To me, that's not what are these local maxes, but what is the greatest max? So let's think about this. If I were to integrate from 0 to 10, I'd start with this negative amount, and then this maybe to here. This would cancel out all of that, and then from wherever that point is until 10, I'm getting all that positive area. And what about at 0? Well, we know that h of 0 is the integral from 0 to 0, and that's 0. Well, so if h of 0 equals 0, I grant that that's a maximum value. That's at the max on h at 0, and then h of 10, well, is going to be the integral, which is going to be all this space here. And that's definitely positive. So I'm going with at x equals 10, h has a max because, and I probably want to do my endpoint justification, but I also want to show that, because h of 10 is greater than h of 0, or we could say that as the integral from 0 to 0 of h is less than the integral from 0 to 10 of h. That would work as well. And I probably want to throw in there also max on h at x equals 10, because to the left of x equals 10, h prime is greater than 0, and x equals 10 is the right endpoint. Okay? All right. So let's move on to 59. There was a part F, though. It asked where the min was, and we had already figured out where the min was, so I'm not going to worry so much about that. Instead, I'm going to give you this graph. That's 3. This is 6, 6. This is 7, 6.5. And this is 9. And we're told that this is a graph, again, of f of x. And we're told that s of t, s of t equals the integral from 0 to t of f of x dx. And so I'm supposed to understand this s function as position. And just like in the last problem, please don't start reading any of the questions until you understand what you're looking at. This is f. This is f. If I integrate f, I get s. That means this must be the derivative of that. So s prime, or v by its more common name, is f. Okay, so I'm looking at velocity. This is velocity. You need to come to that understanding before you get lost in the questions. Okay, part A, what's v of 3? Oh, well, because I know that I'm looking at now a graph of velocity, I can say, okay, v of 3, this is the velocity graph, this f graph is 0. The y value at 3 is 0. B, what about, is acceleration greater than 0 at t equals 3? Acceleration at 3 greater than 0, question mark? Well, let's think about that. We know that a equals v prime. So acceleration is represented by slopes on v. At 3, slopes are positive. So, yes, a of 3 is greater than 0 because A equals v prime, or the slopes of v, and at t equal to 3, the slope is greater than 0 on v. There we go. Okay, so that's part B. Nice. What about part C? S of 3. This is not position. This is not position. We're looking at F. We're looking at velocity. S of 3. Well, I know, because I know the fundamental theorem of calculus part 2, that I can write this. This is FTC2. The antiderivative of velocity is position. Okay? And so, what can we do here? Well, you know, our position function is this integral. If I want to know position at 0, I'm plugging a 0 in for time. The integral from 0 to 0, it's a big old 0. So S of 3 minus 0 equals the integral from 0 to 3 of v of t dt. Okay, so that means S of 3 is integrating this graph. But look, I have some negative stuff. It's all negative until 3. And I think I'm supposed to understand that this f function isn't a parabola, but is instead linear for this part. That we actually have a piecewise function. And without knowing that, I'm not sure I'd be comfortable coming up with this integral unless maybe I tried to write some sort of equation of a downturned parabola. But I'm going to actually go with that's linear there. Okay, so if I want to know the area of this triangle, well, at 0, see, I have to write the equation of the line anyway. So I have the point 3, 0, I have the point 6, 6. That means I'm going up 3, and over, no, up 6 and over 3. Up 6 over 3, slope is 2. So I want to write the equation of the line that has the point 3, 0 and has a slope of 2. Okay, so y equals 2x plus b, and we'll plug in that ordered pair. 0 equals 2 times 3 plus b. It looks like b is negative 6. So then my equation of this line segment becomes y equals 2x minus 6. Now, what I need in order to find the area here, I know this distance is 3. But what about this distance? I want to know what the value is at 0. So if I plug in a 0 here, 2 times 0 is 0, minus 6 is negative 6. So what can I say here? I can say that this is going to be 1/2 base of 3, a height of negative 6, and so I get negative 9. So I know that the integral from 0 to 3 is negative 9. And therefore, S of 3 is negative 9. And don't box in your answer. All right, what's next? When does the particle pass through the origin? Right, when does the particle pass through the origin? Well, and that's an excellent question. So, no, not at 3. Because we need the origin. The origin is when position equals 0. Not position at time equals 0, but when position equals 0, the particle is at the origin. Okay, so how is position defined here? Position is this integral. So I want to know when that integral is equal to 0. Well, let's think. We integrated here and got that negative 9. But once I get past 3, if I keep integrating, I'll get a positive 9. And the positive 9 plus the negative 9, they're going to cancel each other out, and make equal to 0. And that's exactly what happens at t equals 6. So when does the particle pass through the origin? Particle passes through the origin s equals 0 at t equals 6. Now they don't ask me to justify this, so well, I'm not gonna. But if you wanted it, I'd say because from 0 to 6 of f of x dx equals 0. When is the value of this integral equal to 0? Because that's going to tell us when position is equal to 0. Great. That was D. How about E? When is acceleration 0? When is acceleration equal to 0? That's our part E. Well, remember, acceleration is the same as v prime. And we're looking at a graph of v, right? V is this f graph. So when are the slopes on the graph we're looking at equal to 0? Well, the only place I have a 0 slope that I can see on this graph is at t equals 7. At t equals 7. Okay, when is the particle moving toward the origin or away from the origin? Well, let's think about this. So at time equal to 0, we found out that s of 0 was 0, and we found out that s of 3 was negative 9. So we were at the origin, and we moved to the left, we moved to the left, we moved to the left, we moved to the left. We stopped moving when we got to 3. And we had moved 9 to the left. At that point, the particle stops, velocity, this graph, has a 0 velocity, stopped moving, and started moving in the opposite direction, moved back to the right, to the right, to the right, and we determined that when the particle got to t equals 6, the particle was in fact back at the origin. So I moved away from the origin, or the particle did, on 0 to 3, and toward the origin on 3 to 6. But wait a second, I moved to the right, moved to the right, moved to the right. I got back to the origin, and now I'm moving to the right, moving to the right, moving to the right, and I keep moving to the right. But this was the origin, and now I've kept moving past the origin, so I'm again moving away from the origin. So I'm going to say union 6 to 9. Okay? And G says, is S of 9 to the left or right of the origin? Well, we just sort of talked about that, didn't we? We said that at this moment in time, at 6, this area and this area had canceled out. So we were at the origin, and we moved to the right, and we moved to the right, and we moved to the right. And sadly, moving to the right is defined as positive. But here we say, yes, is S of 9 to the left or right of the origin? We know that S of 9 is to the right of the origin. And if we had to justify that, I'd say because the integral from 6 to 9 of f is greater than 0. Okay? So really, I think you should practice some problems like that. Trust me, you'll need them, not just on our test for Chapter 6, but also definitely on the AP exam. All right? Okay, well, I hope this was helpful, a useful review, and I look forward to seeing you in the next video. Take care, everyone.